Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. Today is our lecture number 11, Unit 11, Electrostatics. In today topics, we will study the combination of the capacitors, and then there are rather three types of combination: series combination, parallel combination, and complex combination. Complex combination is actually the combination consisting of both series and parallel together, but there is not much on your book on this topic, so this is why I am not going to explain that too. But anyway, I will tell you that how to solve that complex combination in a simple way at the end of the series and parallel combination, inshallah, if I remember. And the second important point is the electric polarization. So let us start with the name of Allah Almighty. So our first topic is the combination of, it is the combination of what? The first topic, combination of capacitors. So let us start with the combination of capacitors. There are two combination, as I told you. One we call the series combination of the capacitor, and the other we call the parallel combination of the capacitor. So first of all, I just want to do the series combination of the capacitor first. As you see in the diagram, that let me first tell you brief that what is this, why we need a combination of the capacitor, right? For many reasons. The first reason is, for example, if you need a particular value of the capacitor, for example, if you want to, let's see, for example, if you want to have the capacitor of 2.21 microfarad in your calculation. So maybe the industry is not going to manufacture this kind of capacitor for you. Why? Because you know that there is a lot of numbers between 2 and 3, infinite number. So the industry cannot manufacture all kind of combination. So all kind of the capacitor, sorry. So if you want this kind of capacitor which has the capacitance 2.2 microfarad, then definitely you will combine the capacitor two or more in a way that you get the resultant capacitance or the equivalent capacitance is 2.21. One is this thing. Second, we need the combination of the capacitor to we need the combination of the capacitor to reduce the circuit. Third, we need the combination of the capacitor to have the desired value of the charge store or the potential difference, right? Because in a different arrangement, we have different physical quantities, right? The main theme is for our lecture is we will look for the equivalent capacitance of the capacitors in the combination. Sometimes charge stored by each capacitor, charge stored by each capacitor. Third, our greatest important is the potential difference across each capacitor. We will look for this too, right? And the total charge supplied by the battery also, the Q equivalent. As we have the equivalent capacitance, so we have the equivalent, yeah, the total charge supplied by the battery, the total charge, the Q equivalent. We may also have this thing. So we will look at how we can get these sort of the combination, right? So first of all, let me introduce to you about the series combination. For the series combination, few very specific important characteristic of the series combination, and that few important step of the series combination. First of all, that there is only one path for the flow of charges. There is only There is only one path forward for the flow of charges. The flow of charges. What does this means? That if you have the total charge supplied by the battery is Q. So this total charge Q equivalent, this will be equal Q1 will also, the capacitor will also store the same amount of charge Q equivalent, that is the Q1, or if you say Q2 or Q2 or Q3, then all the Q1, Q2, Q3, and if you have not three, rather n number of capacitance, then they will be the same. What is the reason? Because the law of conservation of charges says charges are neither created nor destroyed. Since there is only one path for the flow of charges, one path only, as you see. So look, the charge, the battery, see here, look, there is only one path. So every capacitor have the same amount of charge on them. For example, if the battery remove 20 coulomb of positive charge from the plate A of the that is from the plate A of the capacitor, like from this plate. These are, sorry, the points. I will just label this the plate X, for example, and this the plate Y. So if the battery remove 20 coulomb of charge, then electrostatic induction, you have 20 coulomb of charge, negative charge here. Because of the electrostatic induction, like charges attract and unlike charges repel. So in this region, again, you have the 20 coulomb of charge. Again, because of the phenomena of electrostatic induction, the free electrons in the wire and the plates tends to move forward, and the positive charge move pushed backward. So what will happen? You have the negative charge appear here in 20. So 20 coulomb of charge, 20 coulomb of charge, and 20 coulomb of charge here, 20 coulomb of here, and 20 coulomb of here. So that is the first step, that there is only one path. Second, that all that is the B important point, that all the components, yeah, all the capacitors are connected in successive order. They are connected in what? In successive order. Successive order means one after another, right? It doesn't make if the capacitor is here or if it is here. Why? Because path is the same. So that is, it will be in the successive order. And the third important point is in this combination, that here, if you just see, look, in this situation, that is voltage drop, yeah, IR drop, yeah, voltage drop. Sometimes we call it the IR drop, but here it is capacitor, so the IR drop word is not good. So the voltage drop across each component in the circuit, across each component in the circuit is what? In the circuit is different. In the circuit is what? Is different. If the capacitors are of different capacitance. Why? Because what is the reason? The reason which I have here is because if you look, Q is equal to what? Q is equal to C into V. So as you see that, look, if you have what? That if you have in this case, that for same Q, what? For same Q, if you have different capacitance, then definitely you have different V, right? You have what? You have different V. And this will equals this voltage. It will be equal Q by what? It will be equal Q by V. So sorry, Q by C, right? It will be equal to what? It will be equal to Q by C. So look, for example, that if that is, look, just see, for example, if you have this, let's say 6 coulomb, right? And if you have 3 coulomb of charge, the other 3 microfarad capacitor, 2 microfarad capacitor and 1 microfarad capacitor, then definitely you know this you need 6 coulomb. This need 6 coulomb. Why? Because the battery can only supply 6 coulomb of charge, and the charge stored by each capacitor is the same. So then what will be your V as you see? So if this is your Q, if this is your C, then look and see what will be the potential drop for the capacitor C1. The potential across the capacitor C1 will be 2 volt. It will be 3 volt, and definitely it will be 6 volt. What is the result? The result is that the higher the capacitance, what? The higher the capacitance, the higher what? The higher the capacitance, the smaller will be the voltage. The smaller will be what? The smaller will be the potential difference across it to have the same charge stored by it. So that is one of the reason, because if you have one thing constant, then definitely out of these, if your C is different, then V will be different. And if you have all the capacitance the same value, if you just think C1, C2, C3 equals, then the potential difference will be distributed equally. So these are the special characteristics of the parallels, of the series circuit only. Whatsoever is the component for all kind of series circuit, we have one this thing. So let us now move on to the equivalent capacitance in the circuit. So that is our point one. So our point two is the equivalent capacitance. Covalent, the the equivalent capacitance. We have what? The equivalent capacitance for the capacitor. That what will be the equivalent capacitance? So let me do this thing here. I will just copy this here again so that I can explain to you. Best. Let us see here. Okay. Now you see, look, what will be the equivalent capacitance? Now, if this is the parallel circuit, we will always start from the physical quantity that is divided. So as we know that, look, what does this means that the C voltage drop across, that is a very simple sentence I would like for it, that long story short, that series circuit is voltage divider. It is what? Voltage divider circuit. It is what? This is the summary. Now here, as you see, since as this is voltage divider circuit, as the for series circuit, as for series, it is what? And the voltage divider circuit. So the V equivalent, I label this as the V equivalent. So this V equivalent, the total voltage will be equal V1, V2 plus V3, like that. So you see, look, across this each capacitor, look, for this each capacitor here you have V1 potential difference, it has V2 potential difference, depends on the size of the capacitor, V3 potential difference. Now look, so this V equivalent is equal, what is V? V is indeed equal Q by what? Q by C. So Q by C, so Q by C. So C1, C2, C3, why all are different? But we already know that it is what? That it is the equivalent capacitance, like that one. So let me just push these diagrams back so that I can explain the rest. Doesn't leave it. Okay, so see here, what is going to happen at this look. So this V equivalent by Q equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3, or what I can write that, look, we do not have this formula, right, like this one. So definitely it will be the reciprocal, like for example that V equivalent into Q equivalent will be definitely equal to 1 over C, like that. So you see it will be 1 over C equivalent then. 1 over C1 plus 1 over C2 and plus 1 over C3 for n capacitors. Generalizing this result for n number of capacitors, what will be the C equivalent? C equivalent will be equal 1 over C1 plus 1 over C2 plus 1 over C3 plus up to 1 over Cn. So if we generalize the result, then what does this means? That the equivalent capacitor is equal to the sum of the reciprocals of the individual capacitors. And if you just replace this one capacitor like this whole, the combination of these capacitor, instead of this, if you have one C equivalent capacitor, right, the C equivalent, right, like this, the terminal that was A and DB, like this one. So this comes out to be what? Your C equivalent will be equal it will be equal to 1 over C1 plus 1 over C2 plus 1 over C3 and up to what? Up to 1 over Cn. And there is an important result. And that important result is which one? That the equivalent capacitance is smaller. What? Is smaller than what? Then the smallest in the combination. Then what? Then the smallest in what? In the combination. Now, why is it smaller? Seeing is believing. Seeing is what? Seeing is believing. Making all these three together. Look, one interesting thing which I want to show you. Let me use a kind of a different, and look, instead of all these three, you remove this, and this. And what you will be having, let us see. It is very interesting. Look, just change the more colors like this. See here, look, if I just, instead of all these, if I have this one big capacitor, like this one, okay, all the three, instead of these, I have now only one capacitor. So now the area of the capacitor, if you see, look, the area of the plate I did not change. Which thing has got changed? D. And you know that C is inversely proportional to what? D. If you increase the distance, capacitance decreases. So your physics is in good matching with your mathematics. And this, look, your C equivalent is what? Your C equivalent is smaller, right? Why? Because of this effect, as I told. So look at this thing here. So that is one of the important result, that the equivalent capacitance must be smaller than the smallest capacitor in the combination. Similarly, charge stored by each capacitor, for this, as I told you, that the charge stored by each capacitor, charge stored by each capacitor, by each capacitor, and the charge stored by each capacitor is equal to the equivalent capacitance Q1, Q2, since the same amount of charge is stored by the capacitor. And also the total equivalent capacitance, also we can write that the total charge in the circuit will be equal C equivalent. So if you find the C equivalent, and if you know the total voltage or the V equivalent, so this is another interesting formula. So you have the formula this, you have this, you have this, and you already know V equals Q by C1, and this is your V1. Your V2 will equal Q by C2 until your Vn equals Q, it is Q equivalent, right? The Q equivalent into the Cn. So you have three important formulas for the series combination of the capacitor. The equivalent capacitance expression, which I just wrote to you right over here in the simplest form like that one. Okay, so these four formulas can be used to simplify the circuit, right? Now let us now for the parallel combination of the capacitor. Let me do for you the parallel combination of the capacitor. You see, for the parallel, this is the parallel combination of the capacitor. It will be the reverse of the series combination of the capacitor, and in class 10 you might have learned, right? So I will just do it not in great detail but in a simple way, so that I should switch over to the electric polarization. So you see, look here, there is more than one path for the flow of charges. So if you have net the equivalent charges, parallel combination. In parallel combination, all the components are arranged in a parallel manner. There is more than one path for the flow of charges. So it is a charge divider circuit. It is what? The charge divider circuit, as you see Q2, Q3. So all the charges are distributed along the circuit. So definitely potential difference will be the same because they are connected to the same terminal of the battery, every capacitor. So the same voltage is provided. The circuit is charge divider circuit. So definitely when you want to solve, you have to start from what? You have to start from the Q equivalent is equal to Q1, Q2, and Q3. And definitely at the end of the day, you have the resultant as C1 plus C2 plus C3. And what is this result? The result is important, that the equivalent capacitance is the direct sum of all the individual capacitance present in the circuit. So you have the that is, the equivalent capacitance is greater than the greatest capacitor in the circuit, like this one. C equivalent will be greater than C2 and C equivalent will be greater than Cn, contrary to this one where the C equivalent was smaller than C1, the C equivalent was smaller than C2, and the C equivalent was smaller than the Cn. Here the thing is in the opposite direction way. Why? Let us see that. Let me support my logic. If you just see, look, when you remove all the capacitor and when you replace them by a single capacitor, look, instead of this I just make one capacitor like this one, as you see, and this as you see. Now what you see, that you see here that the distance between the plates are not changing. Which thing has changed? Area. And you know that C is directly proportional to area. So this is one of the reason that mathematics and physics both support each other together. So this is why the equivalent capacitance is greater than the greatest capacitance in the circuit. In the rest of the calculation, you can do it at your own convenience. Now, our next important point topic is the electric polarization. It is what? It is the electric polarization. Electric polarization is actually the phenomena in which, let me electric polarization. Let me fit the diagram first here so that I can explain the things very easily to you. Good. And let me paste it here. So the if you remember in my last lecture, I told you that electric polarization, if you remember, that electric polarization, but not the electric polarization. I told you that dielectric, what? That dielectric increases what? Increases the capacitance of what? The capacitance of the capacitor. The capacitance of what? The capacitance of the capacitor. And if you remember, we came across the equation that the capacitance is equal epsilon naught for the when there is a dielectric medium in E. And this simplifies that if we introduce a dielectric, then what happens? The capacitance increases. This is the permittivity of the dielectric between the medium, and this is for vacuum, if you remember, for vacuum. So now what is the reason? It is because it is due to the fact that because of what? Now I will write it is because of the phenomena of electric polarization. What? Electric polarization. Now what is that electric polarization? The phenomena of the electric polarization is in fact what? The it is the that the when the molecules of the dye, that is the action of the molecules, the it is the fact that when the molecules what? When the molecules of the dielectric, what? Of the dielectric means the insulator, the medium, act as dipole in the presence of what? In the presence of external electric field. External electric field. This effect is called what? This effect is called the electric polarization. This increases what? This increases the capacitance of the capacitor. How? Let me tell you. For example, look. Normally, when you do not have the electric field around this, is in this way. Like, for example, if it is what? If there is no electric field, then what will happen? That for this capacitor, right? That is the each molecule with the positive charge and an electron tends to move, or the positive charge part of the nucleus, the positive charge part of the nucleus of each molecule, and then there is electrons that moves around the nucleus, or like that for the solid. Now you just see that when you apply the external electric field, as you see the external electric field, I will just let me do it with the pen, the greater stress lock. You see, this is the external electric field. As you see, look, this is E, the external electric field. And since this is a bit, it is connected with the positive terminal of the battery. And if this is connected with what? With the negative terminal of the battery. So you have all the positive charge on this plate. And you have what? All that is here, you have the same negative charge on it. So the external electric field E is in this direction. Now each dipole produced a tiny electric field in the direction. This dipole, the dipole produces what? The dipole is the slight displacement of each molecule in what? In the into the positive and negative charge part in the presence of external electric field. Each dipole produced what? Produced a tiny electric field, a tiny electric field in the direction opposite to the external electric field. External electric field, right? So what happens? Your this net electric field E external, or the net electric field, it decreases. Why? Because you just see, look, what is the total, the net electric field? One, because of the dipole. You see, each dipole tends to produce its own electric field in this direction. It is in this direction because of the dipole 1, dipole 2, like this, like this, like this. like this and like this. And what does this opposite electric field cause? It reduces, this causes the electric field. And what is the result? The result I would like to write here. Result. What does it results? This results to, that is, cause or decreases. What decreases? The net elect external electric field E. E decreases. Now look, if E decreases, then what does this means? Look, as you see, as we know that what is C? C is equal Q by V, for example. And you already know that C is equal Q because Q is the same, that is same according to same as per law of conservation of charge. Law of conservation of what? Conservation of charge. So we have only left with V. Now, what is this V? V is equal to E into D. So you know that as E decreases, then what happens? Then V decreases. Then V what? V decreases. And therefore, C might have increased. C might have increased. So this is one of the reason that because of the electric polarization, the net electric field E decreases. If E decreases, V decreases. Since Q is the same, so it means that C might have increased. Now why E decreases? Because, but as we know that E is equal to what? Sigma into epsilon naught, right? And you know that it is the same for the medium, right? And this is what, sorry, I'm so sorry, this is what, this is sigma, this is what? Surface charge density. What? The surface charge density. So that is, E is decreased means they decrease in what? Surface charge density. Decrease in surface charge density means more space have been there for the charge to store. So that is one of the reason. The result, another result, that electric polarization, that electric polarization increases the capacitance, the capacitance of the capacitor. So this is our today lecture. Hope you might have learned from today lecture the combination of the capacitors, why the combination of the capacitor is important, right? And then you have learned the electric polarization of the dielectric. It is the medium between the plates of the capacitor. Now I got, remember, as I told you that I will be telling to you about the complex combination, that I put an extra complex combination of the capacitor, complex combination. In the complex combination of the capacitor, you have both the series plus parallel together, right? For example, if you have a situation like this, one capacitor, another capacitor, and this is, for example, another capacitor. And if you have one capacitor like this, and if you have one capacitor like this, and you just see, look, this sort of the combination is like what? It is like the C1, C2, C3, C4, C5, and this is V. If such situation arises, parallel part must be solved first. Bas. Parallel part must be solved first in order to find the equivalent capacitance, right? Then the series part, and then the final single circuit. So continuous reduction of the circuit into a single circuit. Okay, so this is our today lecture. Thank you very much for being here.